are not a lot of people here. I guess I scared everybody away last week with the analyzing evaluator or something. But speaking of which, on page 41 of volume 2 of the reader is this page called Exit Information, which talks about the final exam, and in particular, what you need to know about all the different evaluators we're looking at, of which there have been several, and a new one this week. You could ignore the part about the non-deterministic evaluator, which we didn't do. But other than that, what it says, it tells you, you know, for this evaluator, you're supposed to know how it works, and for that evaluator, you only have to know how it behaves. All that's in the exit information sheet. Also in there is be a lab assistant. Let me put in a plug for that. Next semester, if you like the course, we always need lab assistants. A lab assisting is an unpaid position, although you can get credit for it, 1 unit per 3 hours per week of lab assisting. But also, if you want to apply for a paid position down the road as a reader or TA, we give preference to people who've lab assisted, both as a bit of a reward for doing so, and also because the more times you've been through the course, the better qualified you are to read in it or to teach it. And finally, letters of recommendation. It basically says, when you're applying to grad school, if the best you can do for letters of recommendation is that you got a good grade in a freshman course 3 years ago, the people who read your application will figure that out. And you should really try to get letters from people with whom you work down the road rather than me. Nevertheless, I always do get people asking for letters because presumably everything's gone downhill from there for them since this course. And you know, I write a nice letter, but all I can say is this person took my course and got this grade. Unless I really get to know you because you're on staff or something, or you do research project with me, then it's different. Okay. This is a course about programming paradigms. We've been through 2 major ones, functional and object-oriented, and we had just a look at client-server. And now we're going to have just a look at declarative programming or logic programming, which is a really, really neat idea in which you don't have to write a computer program at all. There's no sequence of steps. You're not telling the computer, do this, then do this, and what's the value of this. Instead, you just tell it things you know, and then you ask it questions, and it figures out the answer. So it's very magical. The most popular logic programming language in the world is called Prolog. If we wanted to teach you a whole other language, we would use it. But Abelson and Sussman just did a very simplified logic programming system in Scheme. And that's what we're using. So to assert things, to tell it things, you say assert bang. This is a sort of a special form of the query language. Ryan likes hot stickers. Assertion added to database. So let's put in a few more. Okay, so here's our database of assertions. And now I can ask questions. A question is something that doesn't start assert bang. So I'm going to ask question mark who likes hot stickers. And in this system, a word that starts with question mark is a variable. and everything else is just text. And we get the answer, Jordy likes pot stickers. We get the answers, Jordy likes pot stickers, Brian likes pot stickers. Right? So this is the first thing to note about logic programming, is that you don't just get one answer. In this case, we got two answers. In some more complicated cases, there may be infinitely many answers. We don't have a system where that would happen yet, but it's theoretically possible for stuff we're going to learn in a bit. So I can say, Brian likes question mark what? By the way, I'm trying to use meaningful variable names here, but as always in programming, the query system doesn't care what name you use. It could just as well be X and Y, as well as the query system is concerned. And we get Brian likes pot stickers, which is a little interesting because Brian also likes ice cream. So why didn't it tell me that? And the answer is that this system works by pattern matching. So if I ask the question, Brian likes what? The way pattern matching works is for a list, you match the cars and you match the cooters. So recursively. So it's a potentially deep recursion. Although I don't think it will be for the queries that we're going to use, mostly. We'll see. And the way you match a non-pair is two things match if they're equal, and something that starts with question mark in the query basically matches anything. Okay? So this does not match Brian likes ice cream because, okay, Brian matches Brian, and then we have to look at the cooters, and we find likes matches likes, and then we look at those cooters, and we find question mark what matches ice, and that's fine. Then we look at these cooters. This one's the empty list, and this one's a pair, so they can't match. Those just don't work. So we could solve that problem by taking advantage of the notation that we have for improper lists. So I'm going to ask the question, Brian likes dot question mark what? And now I get both answers because this query is, instead of this, Brian likes dot what is this. So the cooter is question mark what. So Brian matches Brian, likes matches likes, and question mark what matches anything. Namely, it matches this entire list structure. Okay, questions about that so far? Who's with me? Awesome. Who's not with me? Nobody. Okay. That's great. That's not the way we usually solve the problem. Usually we solve the problem by taking ice cream and putting it in a list. So the assertion would always be Brian likes, and then one thing, a list of length 3. And in fact, what we really do is this. We say likes Brian pot stickers, likes Brian parenthesis ice cream. Oops. Ah. Uh-oh. Now I'm in trouble. Whoops. Oh, yeah. All right. Let's try again. Assert. Thanks. Brian. I'm afraid it actually took that assertion, though, but we'll see. There we go. So usually what we do is we take the name of a relationship, like likes, and that comes first. It's just a convention. As far as the query system is concerned, it treats every element of the query the same way, every sort of car of a list the same way, or cooter of a list, for that matter. But people find logic programs more readable if you put a relation first and the sort of arguments to the relation after that. So likes is a relation between two things, a person and a thing to like. So now I can say likes, well, likes Brian, what? Yeah, see, it did take it twice. Never mind that. Pretend that isn't there. Or pretend it's only there once. Although it does point up a problem, which is that if you have the same assertion in the database twice, it'll find it twice. I can say likes who, what? And then we also find out what Jordy likes. If I say likes XX, however, I get no answers. That only works likes Narcissus. Now I can ask the question likes XX, and I do find that. So the point of this is that once a variable has been matched in a query, any repeated occurrence of the same variable in the same query has to have the same value. Okay, everybody get that? I think this is all pretty simple so far. Let me say a word about relations. Up to now, sort of the bedrock of our approach to almost everything has been functions. And a function connects input values, arguments, to an output or return value. And that return value can be anything, but what makes it a function is that every time you call the function with the same arguments, you always get the same value. So putting that more broadly, with functions, there's only ever one answer to a given question, right? Relations are different. There can be dozens of things that are in the relation likes with Brian. There can be, lots of people who like the same thing. Who likes ice cream? Yeah. So a relation, one way of looking at it is that it's a Boolean function. predicate function, I should say, that returns true or false. So a relation, you give it a bunch of input values, and it's either true or false that this relation holds among these values. So what in functional programming we would think of as the answer is instead just one of the arguments to the relation. Does that make sense? Footnote, if you're a mathematician, you think about it differently. If you're a mathematician, first you define what a relation is. And then you say, well, a function is a relation with certain constraints. So you can do it either way. But for programming purposes, I think it's easiest to start with the idea of functions, which you've seen before. Actually, you've seen relations before back in high school algebra. Relations are things like less than or equal to. And in math notation, you put the less than or equal to in between two values. But we move it out to the front for the same reason that we moved function names out to the front, like plus. Namely, you can have any number of arguments. So we will have complicated relations among 4 different things. So for example, division is a relation among a dividend, a divisor, a quotient, and a remainder. Okay, so this is integer division. So this is true if dividing the dividend by the divisor gives that quotient and that remainder. Okay? But relations in general can have many, many different ways to satisfy them. So 3 is less than what? Okay, that would be an example of something with infinitely many possible answers. 3 is less than 4, 3 is less than 5, 3 is less than 6, 3 is less than 1,000,000, 3 is less than a Googleplex, and so on. So in principle, if I could put in that relation into the system and then ask 3 is less than what, I should get out an infinite number of answers. Okay? Okay. So far, this is probably seems pretty boring and limited to you because the system only knows exactly what we told it. So any question that I ask, I have to have already provided exactly this answer. So if I say, it tells me that Brian hates cheese, but you know, that's really inadequate. Brian hates racism, and Brian hates Led Zeppelin, and you know, I mean, there's lots of things that Brian hates. And similarly, there's lots of things that Brian likes that the system doesn't know about. It doesn't know Brian likes the Beatles. Okay. We'd like to be able to generalize this a little bit. So I'm going to put in a little bit of data here. Oops. Did that work? Probably not. Yeah, it did. Okay. Right. So so-and-so is the parent of so-and-so. Yeah. So now I can ask who Brian's parents are. I get two answers. And I can ask who Brian's children are. I get one answer. But I can do more than that. I can also do this. Here's where it starts getting interesting. So there's a special kind of assertion that I can make called a rule. Oops. There. This isn't going to work. We'll see. Okay. Let's see if it worked. Yay, it worked. Okay, so the important thing to note here is that I didn't tell the system explicitly that I have a Grandpa Joe and a Grandma Minnie and a Grandpa Max. The system inferred that, derived that, from information that it had about parenthood plus this rule. So rules are the logic programming equivalent of procedures. So a rule looks like this. By the way, don't be misled by the fact that we have parentheses around anything. In this query system, we are taking advantage of Scheme's read mechanism that turns stuff in parentheses into box and pointer diagrams. But we're not using Scheme's evaluator. There isn't a procedure called rule that we're calling. There isn't even a procedure parent or a procedure grandparent. All of these things are just essentially strings of text, although you know what they really are is lists, being matched one against another. So the way rules work is this. Well, first of all, when you type in a query to the query system, the first thing it does is look for assertions, non-rules, in the database that exactly match the query, exactly in this sense of question marks matching anything. And any assertions like that that it finds, it gives you as a result. So if I had made any direct assertions about who's the grandparent of whom, then we would see those. Then it looks for rules. But it can't look for a rule that in its entirety matches a query, because this rule is too complicated for that. It looks for a rule whose conclusion matches the query. So my query was grandparent question mark who Brian, and this rule says grandparent question mark old question mark young. Do those match? Yeah, they do. Grandparent matches grandparent. Question mark who matches question mark old. and Brian matches question mark Young. Okay? So the query I asked does match the conclusion of the rule. If that isn't true, then we just skip over that rule. But if it is true, if the conclusions match, then we take the body of the rule as a new query to evaluate. And I'd like you to understand, I hope you should just instantly understand, but if you don't, let me help you understand, that this business of set up the values of variables, old and young, and now evaluate the body, that's a lot like how Scheme handles a procedure call. It's a little bit different because it's the query evaluator, not the Scheme evaluator, that we use to evaluate the query. And the result of that evaluation is true or false. So we want to know, is this true? This is the body of the query. And is like a special form in queries. And or is another one, and not is another one. So assert, bang, rule, and or not, those are the only kind of reserved words in this system that have special meanings. So what and means is if all of its sub-expressions are true, then this is true. So it's a lot like the procedure, well, special form, and in Scheme, which says return the value true if all the arguments are true. The difference is you don't see true printed out. Instead, what happens is if the result is true, then the query system says this is a match. And what's actually printed out is the original query, but with specific values substituted for the variables. So the query was grandparent question mark who Brian. And every time it succeeds in matching that through the use of this rule, it prints out grandparent so-and-so Brian by finding out the value of who. So now what it has to do is try to match two queries about parent, namely parent question mark old question mark middle, parent question mark middle question mark young. But just as in Scheme evaluation, queries are evaluated in an environment. The environments are a little different in details, but to a first approximation, it's the same idea. So when we matched my query, grandparent question mark who Brian, against the conclusion of the rule, we came up with some constraints on these variables. So question mark who has to be the same as question mark old. We don't know who it is yet, but whoever it is, they both have to be the same. And question mark young has to be Brian. Okay? So now we look for parent question mark old question mark middle. Since we haven't yet constrained either old or middle, we're seeing middle here for the first time. Every single parent assertion in the database will match that first parent clause in the and. It's just parent, variable, variable, and we get every single one matches. So, parent, Tessa, Bob, matches. But then we have to also satisfy parent, question mark middle, question mark young. So in the case parent, Tessa, Bob, we've bound Tessa to old to Tessa, I should say. We've bound middle to Bob. And now we have to match parent, middle, young. Middle and young are both bound. Middle is Bob, young is Brian. Is Bob the parent of Brian? No, he's not. So we reject that particular set of bindings. Now we look and we find another assertion in the database that says parent question mark mini, I'm sorry, not question mark, parent mini Tessa. Okay, fine. Old is mini, middle is Tessa. And now we're looking for an assertion that matches parent question mark middle question mark young, but middle has to be Tessa, it's constrained, it's bound already, and young has to be Brian. So we're looking for an assertion parent Tessa Brian, and we find one. Tessa is my mom. And as a result, this line is printed as a result of that set of circumstances. Yeah? So would it be more efficient if the two and clauses were flipped in order? It would for this particular query, but remember you can also ask the question, grandparent mini question mark who? And for that it wouldn't be more efficient. But it's a good thing to think about. And sometimes it's a crucial thing to think about because what you get is so inefficient that it never gives you an answer at all. It sits there looping. So we're going to see some things about that coming up later on. Okay? Any further questions about this parenthood example? Yeah. Sure. Grandparent, oops, question mark X, question mark Y. There they are. Okay. By the way, when a variable is used twice in a query, I told you they have to match the same thing both times. Like if I had said likes question mark X question mark X. For a rule, the same thing is true. Once a variable is bound in a rule, any later uses of that variable have to agree with the first one. But it's not true across queries or across rules or even across invocations of a rule. So if I want to know about great-great-grandparent, I might have a rule that says, you know, this person is the grandparent of that person, and that person is the grandparent of another person. And then we might end up looking for grandparent a couple of times, and there'd be different bindings for young and old each time. So it's only in a particular application of a particular rule that a binding is in scope. That's still a little vague. We're going to talk today, we have talked today, and we'll finish talking today, about what you can do with the query system. And on Wednesday, I'm going to try to clear up what I'm sure is some uncertainty about how it actually works. But first I want you to appreciate what it can do. So it's looking at a huge abstraction today from above the line and Wednesday from below the line. Okay. So I used grandparent and parent in my example. A more complicated example would have assertions, mother and father, and would have a rule like this. Okay, so here's a new rule. It says somebody is somebody else's parent if either they're the person's mother or the person's father. And we could use this rule along with assertions about mother and father to do a whole family tree thing. You can ask, is somebody my cousin once removed? And all those things that you never remember what they mean. But the database could figure it out. So this is a database-y use of the query system. And in the book, their first example, I think, of the query system is also kind of database-y. They put in data about the employees at a company, a fictitious company, and their job titles and their salaries, and then you can ask various questions. And something like this, a different notation, but this basic idea, is how database systems work in the real world. You can ask queries with ands and ors in them, and you can invent rules and all sorts of things. Yeah? Okay. What predicates, is the question, does this implementation of logic programming have access to? I'm going to give you two answers to that question. The elegant, logically correct answer is none. All it knows about is pattern matching. And any relations you want, you have to build. The quick and dirty, grubby answer is, in this implementation, there is one, I lied, there's one more special keyword called Lisp value that lets you evaluate any Lisp predicate. And they use that for questions about who makes more than $40,000 a year. But you should try to avoid using Lisp value because you end up leaning on Lisp to do all the work for you. We can, in fact, invent arithmetic purely in the query system. And we actually do that for positive integers. And if you look at some of the old exam questions in the course reader, there's things like invent plus. You represent the number 5 as the sentence A. Okay, so that's how you represent positive integer, non-negative, I guess, integers. And then you can build addition and subtraction and multiplication and division on top of that system. Let me note, you don't have to build subtraction separately from addition. Because supposing you have addition, you can ask questions leaving out, using as a variable any piece of the relation. So you would have a relation like that would be true for something like add 3, 4, 7. So notice the difference between a logic programming relation and a scheme function. And the scheme function would be add 3, 4. That would be the question you ask. And you get the answer 7. In the query system, you ask the question, adds up to 3, 4, 7. And the 3 numbers would be like arguments to the relation. And what the relation tells you is, yes, that's the case. 3 plus 4 is 7, or no, it's not, if you asked it a question that was false. Okay? So your relation will have one more component to it than you're accustomed to in functions. Like take even parent. If we were writing a parent function in Scheme, it would be, well, let's talk about father and mother, where it's more or less unique, apart from exceptions. There'd be a function, parent, quote, Brian, that would return the answer, no, I'm sorry, father, quote, Brian, would return the answer, Leonard. Mother, quote, Brian, would return the answer, Tessa, and those would be unique answers. Note, by the way, in Scheme you say, quote, in front of constants. In this query system, you don't quote constants. Instead, you question mark variables. So it's sort of the default thing for a word to mean is a constant rather than a variable. And note also that these names of relations, they're just words. So here, in this rule, I put the relation first, but I didn't have to. I could have said rule question mark old, parent, question mark young, and then, the same thing further down. The query system itself really doesn't know anything about what's a relation and what's an argument to a relation. All it knows about is pattern matching. And it's really quite surprising that that turns out to be enough to do computing. And we'll talk more about that part of it on Wednesday, how amazing the algorithm is. Yeah? I'm sorry. Oh, yes, the order certainly matters. Yeah, absolutely. So for instance, earlier I put in two different kinds of likes, one infix and one prefix, and they didn't get the same results. Okay, here's the fun part. Okay, look down here. This is a piece of scheme code. It's the procedure append. Takes two lists. It says if the first list is empty, return the second list. Otherwise, cons the first element of the first list onto append cdr of the first list to the second list. Right? You've seen this before back in chapter 2. And it should all be totally familiar to you. So now look up here. Where it says AA, pretend it says add assertion. This is because the query system doesn't have a load command, but scheme does. So AA is a scheme procedure that is equivalent to the assert bang thing in query system. So here are the rules. There's two rules, this one and this one. And as we talk about them, I'd like you to compare them to the scheme code. So the scheme code has two cases, the base case and the recursive case. And the two rules correspond to those two cases. So the one that's highlighted now corresponds to the base case. In the scheme code, the base case says, if A is empty, return B. This rule says the relation append holds for the empty list, any list y, and that same list y. In other words, if you append the empty list to anything, you get the anything. Okay? Everybody clear on the relation, on the connection between this append rule and the base case of the append program? Okay, a couple of sidewayses. Somebody ask a question. So we're comparing this rule with just this much of the scheme code. If the first argument is empty, return the second argument. This says if the first list is empty, and here's the second list. This is like B. It's like this is the A value, this empty list, and this variable y is the B value in the original scheme code. So empty list appended to B gives B, and the same thing here. Yeah? Okay, I'm going to move on. Now let's look at the other rule. That's a little more complicated. First, we'll look at the scheme code. What if A isn't empty? This says split it up into its first element and the rest of it, its car and its cdr. And we're going to recursively compute append cdr A B, and we're going to stick car of A in front of that. Okay? And that's going to be the result. So the result of append where the first argument is not empty is a pair, because cons makes a pair. the car of this output pair is the car of the first argument. The cdr of the output pair is the result of doing this append. Okay? So now let's look at the conclusion of this rule. So first of all, this rule applies only in the case where A is a non-empty list. Right? That's like the if in the scheme code. Only if null A is false do we get to that cons. So since the first argument is non-empty, we can think about it in terms of its car and its cdr. That's what this is. This is scheme dotted pair notation. It says this argument is a pair whose car we're going to call U and whose cdr we're going to call V. Okay, so question mark U is car A. Question mark V is cdr A. And then question mark Y is B. Right? Okay, well, we don't have to divide B, I'm going to have to divide Y here into its car and its cdr because the scheme code doesn't divide B into its car and its cdr. The only use of B is right down here. Right? It's the whole B. So A is replaced by this pair U dot V. B is replaced by the variable Y. And now what do we know about the result in this case? It should be a pair, because of that cons, whose car is equal to the car of A. Now, what you're going to be tempted to do, every single one of you, is going to be tempted to say something like question mark U dot append question mark V question mark Y. Right? Because you're going to want to take the cdr of A and append it to B. If I had some red chalk, I'd use it, but I don't, so I'll just do that. There's no composition of functions in query system because there's no functions, first of all, in the query system. So you do that on the final 0 for that question. So what can we do? Well, I don't have an exact expression that I can put in here yet. So I'm just going to make a variable, z, which is the cdr of the result. And then I'm going to assert something about the relationships among these variables that gives me the right value of z. Namely, z should be the result of appending v with y. That's what this says. So if we get a query, an append query, in which the first thing is a non-empty list and the last thing is a non-empty list, and if the cdrs match up, there's this question mark u here and question mark u here. If the same variable occurs twice, it has to match the same thing. And then we evaluate the body of the rule, which is this recursive invocation of the same rule. It says, I want to assert, or in order for this thing to be true, in order for this rule to match the original query, it has to be the case that appending cdr of A to B gives cdr of the result. Okay? And it's a little bit of a convoluted way to think if you're not accustomed to it. But it gives us some remarkable results. I can say append A, B, C, D, E, A, B, C, D, E. Oops, what happened? Did it not load? Wait, I'm really confused. Nope. All right, let's try this again. Oh, I'm still in SDK. Whoops. I'm in variable GDL, but I defined it. Okay, let's try again. Hope this works, because it's kind of the big moment of the lecture coming up. Yes, query results. There we go. So that's not a big surprise. But I can say append A, B, C to what gives A, B, C, D, E. That works. I can say append what to DE gives A, B, C, D, E. And that works. And finally, I can say append X, Y to get A, B, C, D, E. What are all the things I can append to each other to get A, B, C, D, E? And here they are. Okay? Functions won't do that. Only relations will do this piece of magic. Sorry for running over. See you Wednesday.